crypto seminar this week. Hope you enjoy the food, and I'll be talking about another recent work of mine. This is also joint work with Ayush, and the theme is that we explore post-quantum cryptography and especially new assumptions within post-quantum crypto and how we could build new primitives off of them. So if you attended my prior talk, there may be some overlap, but hopefully there isn't much. Okay. So
as long as the reviewers didn't say there was overlap, but there was not overlap.
So in this work, we considered a so-called lossy cryptographic primitive, and the precise name was lossy trapdoor functions. And what we did is that ever since its introduction in 2008 or so, there was no other sort of constructions other than from lattices. And in this work, we changed that by proposing a new construction based on a new assumptions on codes. So that is the one sentence summary of the talk, but let me go into more details. Okay. So post-quantum cryptography, we are actually starting to standardize it and adopt it with major industry adoptions and so on. But at the same time, this transition is going to be many years from completion. And especially what we're missing is a lot of advanced cryptographic primitives, such as, say, threshold signatures, FHE, SNARKs, or even quantum cryptographic primitives. All of them are still the topic of very active research, and we still need all of them to reach adoption. The problem is that when it comes to advanced cryptographic primitives like this, there's not a lot of ways for you to build them. Oftentimes, there's only one, which is using lattices. And even for the case of public key encryption, you'll see there's not many candidates. A lot of the candidates, PKE, have actually gotten broken. So let me give you
Candidates for public key cryptography.
Yeah. Yeah.
Oh, I mean, okay, like
PKE
that's not based.
Which one?
Okay, then never mind.
Okay, yeah, awesome. So the state of post-quantum cryptography is basically, you can think of it as lying in 4 quadrants based on these sort of assumptions that they rely on. Okay, so on one hand, you have lattice-based cryptography, which is based on hard problems in lattices, such as approximately finding the shortest vector in some arbitrary lattice. There's also assumptions on codes, which says that decoding some random codes or some ensemble of codes is computationally difficult. There's also multivariate-based cryptography, which says that solving some system of multivariate polynomial over some finite fields is hard. And isogenies, which are statements about finding isogenies which are just mapped between 2 elliptic curves, and finding such isogeny is hard, essentially. So we have these 4 branches. And
question.
Yeah.
Are there any proposals for ad hoc symmetric solutions, like AES or anything? I'm actually not very familiar.
AES is just
We just assume it is? Okay.
like
Yeah. I'm talking about sort of more structured assumptions that have a chance of being more than just symmetric.
Okay.
I mean, wasn't isogeny stuff like Volga?
Not
Well,
quite.
I think there was some subtleties. At first we thought everything, and then
Yeah.
realized that
Okay.
Yeah, I'll come back to that and try to explain a bit more.
okay, thank you.
So, okay, so here are the 4 main branches of PQC, and let's see how much cryptography we can build from each of them. Okay, so because they're cryptographic primitives, we all get one-way functions, right? It's one-way functions are everywhere. But when you come to public key encryption, then already there's a lot fewer candidates. The multivariate and the isogeny-based ones have many schemes proposed, but a lot of them have also been attacked. And so at the moment, I think there is no candidate for either of them, either of these branches of assumptions that are sort of well-studied assumptions. The only PKE that we know are relatively relatively well are the ones from lattices and codes, and those are also the sort of NISC winners and runner-ups for their post-quantum cryptography competition. Okay, so that's PKE, but there are many other primitives that are more advanced than PKE, and there the situation is even worse. So for something like identity-based encryption, we only know of one solid constructions from lattices, or like a solid type of construction from lattices. There is one construction from codes, but it's very secure. It's broken in quasi-polynomial time, and there is no candidate from either multivariate or XOR. And then if we keep asking about more and more advanced primitives, such as more advanced encryption schemes or advanced proof systems, then lattices are essentially the only game in town. We don't know of any other constructions other than based on lattices. And then for some primitives, such as program obfuscation, we just don't know them in the post-quantum setting at all. Okay.
Really? Oh, because you don't know bilinear maps.
Yeah.
Right, no, there are some candidates of program obfuscation.
I think there's like
So
Not well understood.
yes.
One of my
So
candidates.
yeah, there are candidates, and some of them have not been fully broken, but overall they're not. You cannot base them on like well-studied or even well-stated assumptions.
Right.
Yeah, the scheme is just sort of like what it is. Yeah. Cool. So this work, we don't care so much about this,
Okay.
but we care more about these more advanced primitives for which there's no other instantiation other than from lattices. And you may still ask that, well, we have good constructions from lattices, or relatively good. Why should we care that we should be looking for other constructions? And I think this is a well-motivated problem in cryptography, and let me just offer my 3 reasons for that. The first is that as cryptographers, we always have to look out for the next advances in cryptanalysis. Maybe your favorite assumptions get broken tomorrow, and when that happens, you have to, you better have some alternative to fall back on. And this is not just theoretical, but also there's been a lot of high-profile breaks, or I guess attempted break for the last preprint here, on lattices or other post-quantum assumptions. And so, yeah, I just want to say, even if this attempt on quantum algorithms or lattice problems did not succeed, it doesn't mean that people aren't continually trying to break lattices or all other assumptions. And so I think this is the most important reason why we always have to keep looking out for new cryptography from new assumptions. Okay. The next reason I would argue is that different assumptions can bring with them different algebraic structures. And that alone might lead to being able to build things that we just do not know how to build right. So there are a few primitives that there are a few primitives such as, say, structural permutations, time-lock puzzles, or quantum money that we don't know how to build from lattices. There are some candidates for some of them that are based on, I think, like quantum money. There's a proposal based on isogenies or just abelian group actions with very strong assumptions and so on. But essentially, we just don't know how to build these ones and even others from that. And finally, I just want to say that these assumptions, they come from different areas of mathematics and theoretical computer science. And actually, the fact that we could build cryptography from these seemingly unrelated problems is a very cool thing, in my opinion. And that's also a reason why we should study these assumptions, maybe just for their own sake.
So actually, I'll give you maybe 2 notes on this. So I think the first thing, I mean, when people talk about point 1, they love quoting like McEliece 94, like cryptographers like seldom come up. Yeah, cryptographers seldom sleep. So you can have that if you want. It's like a little cheesy. But actually, I think to me, like the best reason, maybe the most convincing reason for like a general audience to study cryptography from these new assumptions is to try to get better performance. Which, like, you know, we've tried for a long time to optimize FHE from lattices. Like, if we had FHE from codes, like, could it be more efficient? We have better security parameter. Like, I feel like, I don't know. I would include that. I think that's like super strong. But I agree with you.
I agree as well. This paper is not an attempt towards better better efficiency.
Yeah.
So that's why I don't have it on the slide.
That makes sense.
Yeah. Okay. So the study, the main subject of this paper is code-based cryptography, and they are based on this simple heuristic that solving linear algebra problems where you add in a little bit of noise is computationally difficult. Okay. The nature of the noise added to this linear equation S times A determines whether we're talking about a code-based assumptions or a lattice-based assumptions. So essentially, codes, you care about random corruptions of a few coordinates, so the noise patterns are sparse, versus in lattices, the noise patterns are sort of small magnitudes. So you have, let's say you work over some modulo, and then you just plus or minus a small number from the exact number.
I guess there's like probably like a unit, like, I mean, that's like in that perspective, like lattices are codes like over like L1 or L2 instead of like the Hamming norm or something. Probably like a unifying framework. I bet, like, I don't know, have you seen like a paper which was like, oh, the general assumption, which is this, but like for any like LP norm kind of vibe?
Yeah, so the sparse is in L0 norm, and the small magnitude, it can be anywhere from L1 to L infinity.
Yeah.
Yeah.
No, I never really thought about it.
There are also other metrics, but they're not as well studied. And even this formulation is even false for some metrics.
Which ones?
There's some p-adic metric that it fits on.
Oh, okay.
Okay. So the seemingly small difference between the noise model actually lead to a very vast difference of what we can build from codes versus from lattices, and also very different understanding of their worst case partners. So these are average case problems where you sample your matrix A and you sample your secret S at random. But what if you want to reduce these average case problems to some worst case problems on either codes or lattices? If you want some worst case partners like this, the lattices actually have some very good reductions based on from Regev and others. But with code, we just don't know that good of a reduction. So can we try to build more advanced primitives from code-based assumptions? And I think studying this question would lead us to understand more about codes in general.
There's no like average case assumption of like let me work, like there is some code that is part of the code, but not like the average code is part of the code.
So the average code is hard to decode. That's true. But if you want to reduce it to some worst case problem, like if you want to base cryptography on NP complete or something, right? Then we care about worst case problem that you can reduce to. And yeah, there's just not a good reduction with codes at the moment.
Like, wait, what are the problems for lattices? Are the lattices like the worst case problems themselves, like worst case problems on lattices that you reduce to? So like, could you reduce like an average case problem to like worst case problem codes? Maybe that was enough.
Yeah. So people have been trying that, reducing average case, worst case problems with codes, but the reductions have been very bad so far. Like you can reduce very hard average case problem to very easy worst case problem. And we would like this gap to get smaller.
That's interesting.
Yeah. Okay. So our main result of the paper is that we propose a new code-based assumption that we call dense-sparse LPN. So LPN stands for learning parity with noise, which is the assumptions that says essentially that random codes are hard to decode with a little bit of noise. Okay, but instead of random codes, we have a more structured matrix distributions. We call it the dense-sparse distribution. And our initial cryptanalysis suggests that it is resistant to all known attacks. We use our new assumptions to construct a primitive called Lossy trapdoor functions. This is a simple to state primitive. I'll state it in the next 2 slides. And with many applications, so it can just sort of like in a black box way, imply all these other primitives, such as collision resistant hash functions, CCA secure public key encryptions, and so on. And in the post-quantum setting, it was only achieved from lattices from the original paper that proposed the primitive. And finally, the reason why we had to come up with a new assumption is that we tried it from just plain LPN, and we found some barriers. And we had, in order to overcome these barriers, especially in sort of noise management, we have to think of other variants of LPN. And in the course of that, we also found a new attack against another variant of LPN called sparse LPN that people also have been using, but it got broken in the parameter regime that we found necessary to build this primitive. So that's why we had to come up with a new assumption. Okay. So as a result of our work, now we have at least one code-based construction of Lossy trapdoor functions, albeit based on a new assumption.
Does that imply any new primitives from code base that we're not known? Like any, because this is a primitive.
Yeah,
but any
right.
like
some other
cryptographic like public key of some kind or something.
So it also implies, yeah, I would say not too much. Initially, we had hoped that we could build more, but we also run into some difficulties. So yeah, it's an open problem. Yeah. Yeah, also wanted to mention, there is some isogeny-based construction. This is from this line of work on quantum advantage. So if you're familiar, there's this related primitive that imply Lossy trapdoor functions, but with very little lossiness. So a constant number of bits of lossiness versus a constant fraction for our setting. And yeah, I'll also explain what it means to be lossy in the next slide. So for the rest of the talk, I'll first talk about the template to build Lossy trapdoor functions, or LTDF, from general noisy learning problems and why it fails from LPN. And that motivates us to introduce our new assumptions, dense-sparse LPN, and then we'll end with some initial cryptanalysis and lots of open questions from our work. Okay, so Lossy trapdoor functions. It's a function with 2 indistinguishable modes. So it's a key function. You need some evaluation key to evaluate it. And the key is generated from some setup algorithms. You can set it in either injective mode or in lossy mode. In injective mode, the function is injective and it can actually be inverted using a trapdoor. In lossy mode, you have lots and lots of collisions, so that the range of the function is actually much smaller than the domain of the function. And from LTDFs, you could imply all of these primitives here in a relatively black box manner. And so, yeah, I'm not going to go into any of these in details, but suffice to say, people have sort of taken this LTDF primitive and then just showing it implies a lot of other things. Okay. So back to these noisy learning problems again. Here I'll state things in a somewhat matrix form. So S and E are now matrices. You can think of them as just giving out many samples of many noisy samples. And the difference is that, so here the entries of the error are small in the lattice case, and the entries are mostly 0 or sparse in a code case. And that leads to a much different noise budget for lattices versus codes. By noise budget, I mean that how large can the noise get in each of these? For lattices, the noise you can go up to the modulus, which can actually be quite large. It can be even exponentially large in terms of the dimension n of your matrix. Versus in a code-based case, the noise can go up to at most n, because the number of zeros coordinates are upper bounded by the dimension.
Wait, so sorry, what do you mean in terms of, I guess like what you mean is like the noise could go up to blah blah until you just like lose.
Yeah, until you lose functionality, you can't do anything with it anymore.
Right, so it can go up to epsilon m, like the distance of the code.
Yeah, it can go up to O of n.
O of n,
yeah.
The distance. If the code, I mean a random code would have the distance.
Yeah. So yeah. I guess more likely this should be like n over 2 instead of n, but like doesn't quite matter.
Delta.
Yeah. Okay. And if you look at LPN in particular, its security is actually quite well understood. People have been trying to break it for several decades, and the best attacks essentially boils down to this very simple algorithm. You can call it information set decoding, but there's also been different names of it in the literature, and lots of like incremental improvements to this algorithm. But at its most basic, it's just that you try to solve this linear equation using Gaussian elimination, and you will succeed if somehow you pick the right n coordinates that all do not have any errors. So if your error vector is chosen from this Bernoulli distribution, meaning it is 1 with probability epsilon and 0 otherwise, then the time complexity will be exponential in epsilon times n. And we just don't know how to beat this, especially there's a slight improvement, the BKW algorithm, but that only applies for epsilon as a constant. But when epsilon is sub-constant, we don't know how to beat this time complexity. Yeah.
Maybe this is skipping forward a little much, but do you think that your new assumption that a sparse LPN is sub-exponentially secure something like this? Or
yeah.
Do you think this?
Yeah,
Okay.
essentially what this is.
Okay.
Modulo, it's still sub-exponentially secure, but there's another attack that we needed to consider, but that's also sub-exponentially secure.
Okay.
Yeah.
So what's the improvements for constant epsilon? Like, is there a distinct way to explain what that is? Or is that...
Yeah, you can sort of try to pool together many samples, and that gives you like
Pool together.
yeah. Let me just flash you the landscape here. So this is the hardness where if the in the constant noise regime, you have attacks that go like 2 to the n over log n. So we have this log factor in the exponent that's shaved off. And yeah, the idea is that you try to get lots and lots of samples, you add them together, that would increase the noise, but also it sort of gets better in some sense.
Okay.
You can, you should look at it. And yeah, I don't think I can explain it succinctly.
Okay, yeah, that's cool.
Yep. So this is the landscape of LPN and the best attack based on the asymptotic that I mentioned. Okay, so essentially you don't know anything anything interesting until you get to square root noise, inverse square root noise, at which point you get public key encryption and oblivious transfer, which are essentially equivalent. But then you have to go all the way to this quasi-polynomial broken regime where you start seeing other primitives such as collision-resistant hashing or identity-based encryption and so on. But that's like very, very close to broken. And the question you may ask is, where does lossy trapdoor functions fall into all of this?
I like this diagram. Still illustrated.
Thanks. Okay, so let me show you the template to build LTDF. This is from the original paper. So the template is that your evaluation key is precisely the LPN samples. So you take your matrix A, and then you also have B, which is either SA plus E in the lossy mode, or you add in some suitable code C that you use to invert in the injective case. So C is essentially just any good error correcting code.
Wait, how does that work with A though? Shouldn't C need to be dependent on A? Otherwise, you're essentially adding a random error term.
So C is some deterministic code.
Like resolvement.
But A is truly random, right?
A is truly random, yes.
So in that case, you could end up adding a truly random vector as an error. So why would this allow you to correct using the code?
Oh, the error E there, or?
So my understanding is that you take a code word and then you add your LPN sample to it.
Yeah, let me.
So you can treat the whole LPN sample as a code, or sorry, as an error. Right?
Treat the whole LPN samples as an error. I don't think so. So you will try to have some cancellation there. So the A term just gets canceled out.
Okay.
That's the point. So here's, you try to cancel it out. So first, to evaluate, you just multiply x, which you can think of as a sparse vector. So that's the domain of the function. So, and then you just multiply x, multiply the evaluation key with x, and that's your evaluation. For inversion, you try to, if you know s, then you can cross out the terms with A, and then what you get left with is the C times X plus some error. And then the C is a good code with efficient decoding, then you can decode, assuming the error is not too much.
So yeah, so I want to understand this.
Yeah.
So I want to understand this again. So EK is the evaluation key.
Mhm.
Allows you to evaluate the key.
Yeah.
In the lossy mode, there is no trapdoor because you can never invert. In the injective case, I see. So use the S evaluation. I see. So why does the code, or sorry, why does the code make it injective in this case? Is it, I guess I see, I sort of see why.
Yeah, you do the cancellation, and then you get a noisy code words, and then you can decode.
I see. So how would you go about picking this code? Like, what would the choice of the code be?
Any like asymptotically good error correcting codes.
So like read all and fine.
Or concatenated. So I'm working over constant field size here.
Spielman code is good.
Yeah, I would say.
Okay.
Okay. But inversion is not really the point of the paper. The point is that there's lossiness. How do we argue for lossiness? So if you look at this evaluation, you have that essentially the second argument is a function of the first argument plus some nodes. So if you want it to be lossy, then you want, first of all, that the first argument should lose some information about the input, and that the added error in the second argument is not too much. So together, these two facts mean that you achieve you achieve a smaller range than the domain. Okay.
Why do we need E times X to be low errors?
So that you can imagine the first argument gives you some points in the space, and the noise gives you some balls that are surrounding the. Yeah. So
what's S again?
S is just the sequence. S is the trapdoor here. It's some matrix.
Is it a matrix of low rank?
No, it's just uniformly random. We don't care because we can, yeah, it doesn't matter.
So, okay, so we're not focused on actually showing that the lossy code is not injective. Like it could, like how do you know that the function defined in the lossy code is not injective? It's just you don't know how to invert.
No, because the range is smaller than the domain. So any function with that property cannot possibly be injective.
Yeah, so which function has this property here? F?
No, the function f.
Oh, F.
F,
Yeah,
the evaluation.
I see it.
Yeah.
The top line is just parameter or public parameters for the scheme. I got confused on that too. And then you define F using first.
Hmm.
Yep.
Yeah, I still have a hard time requires. So I have a hard time seeing what this function is compressing. So what are the dimensions?
Oh yeah, that's gonna be calculations are on the next slide.
Okay.
Yep. Okay, so we want this to be lossy, and in particular, we care about those two properties. So let's compute some things. Okay, the first thing is we want this path function from x to a times x to be compressing, meaning that the domain size is larger than the range. Okay, so if x is sparse, let's say t sparse, then it's roughly n choose t, right? And which is roughly this guy. And the range is just 2 to the n. Let's say we're working over binary fields. Okay, if you work this out, this means that the sparsity t must be pretty close to n. It must be n over log n. Yeah. And if you try to plug in into how much noise you can hope to get, the constraint here is that the accumulated noise needs to be at most a constant. It needs to be bounded by some constant so that we can actually decode in the injective mode. But the accumulation here is essentially you take the initial noise epsilon and you times by t. T is the sparsity of your vector x.
So I'm not sure I'm fully following, but what about picking a code which has like distance, which is like 1 minus little 1? It is.
Yeah, so that means it has terrible rates.
Yeah.
And that's also not good.
Okay.
For other calculations.
Okay.
Yeah, I'm sweeping. I'm not showing you the full calculations, but like
I believe
you have to. Yeah. Okay, so if t is this large, then epsilon must be very small. Must be log n over n. And in the picture I showed you several slides earlier, this is broken in polynomial time. Okay, this is the simple attack that I mentioned earlier. Okay, so this is why we couldn't just instantiate this template with the LPN assumptions. And so we asked ourselves, could we try to achieve, mostly it's just this compression issue that when you try to work out this equation, you get a very large sparsity T, and that kills your construction. So can we try it with better parameters? And the answer is yes, if we use a new trick by somehow restricting the range of the hash function. So how do we do this? This seems pretty abstract for now. We just change the matrix distribution. So now the matrix A, instead of uniformly random, is going to be very sparse. Let's say each column has only k non-zero entries, and we may choose these k entries at random.
This reduces the noise.
Yes, this reduces the noise growth because when you time it, you still get like a sparse vector, and that reduces the range. Okay, so this sparse LPN, this is also relatively well studied and have found prior cryptographic applications in the past. In our setting, just wanted to keep in mind, we need the sparsity parameter k to be constant or slightly super constant, just so that the math works out. I'll show you in the next slide. But also, when you work with sparse LPN in general, you need to ensure that this m here, this number of samples, needs to be lesser than n to the k/2. Otherwise, you would come into the situation where if you just choose the columns at random, then two columns will repeat with noticeable probability. And when that happens, you can break the assumption. Okay.
I mean, the code is not,
Mhm.
like, the matrix is not full rank, which means, why can you break the assumption?
Oh, because you can find the two columns are the same.
Yeah.
Right? And then you just compare those two columns, essentially. So you compare the two indices with
But then you can figure out.
two, and
You can be like, oh.
So like, if they are the same, then it's more likely that it comes from the LPN distribution versus random, because random is like, they are independent.
Yeah.
Yeah, but here they're correlated. Okay. So yeah, that's that. So as I mentioned, now we have a slightly different calculations where you only care about vectors in the range which are at most k times t stars. And once again, you try to work out these equations. What you get is a smaller noise rate, polynomially smaller to be exact. So you can think of here a random example here, let's say. So k is like 6 and m is n squared. Then you get something like t is roughly equal to n to the 0.8, which is lesser than n over log n. And the same calculation with the noise shows you that now the noise can be inverse polynomial. And the question here is that what is this new parameter regime, and whether sparse LPN is actually secure under this parameter regime. Okay, so let's flash you this graph again, but now with sparse LPN. So with sparse LPN, we also know PKE and OT from a certain noise rate. This time we have to sort of correlate the noise rate with the number of samples, but let's just not care about too much. So if somehow we could have lossy structural functions in this regime, which therefore also implies the other things, then we will be good, right? But unfortunately, it is not the case. This regime right here is broken. Or at least it's broken by our new attack, which we show is it's very simple and should take polynomial time. Okay.
Does that break any schemes? Were there any schemes that were based on?
Actually, no. people just haven't studied this noise regime yet.
Okay.
Yeah.
So you brought out this noise regime and we tried to broke it and then you broke.
Yes. So I guess before this work, it's sort of like what attack could be better, right? We could presumably go all the way to the same log n over n regime that as LPN, but then it turns out it is not the case. And so let me show you why it is not. Okay, so let's say you have some matrix A that is sparse, and you have some vector U that is either like SA plus E or totally random, and you want to distinguish between the case. So the way you would do that is you would try to find some vector X in the kernel of A, meaning that A times X is equal to all 0, such that X is relatively sparse. And the sparsity means that when you do the inner product X and U, then it will be biased in the LPN setting if it's an LPN sample and unbiased otherwise. And you can pick up on this bias. Okay, so the way you build X is that you can just pick some random subset of size L here. So L is some parameter which we will tune later. And then we can find all the columns whose non-zero entries are all in this slice of rows. If there are more than L of them, then you can find a linear dependency, right? Just Gaussian elimination. And so this means that we have such an X, and then we can compute this inner product to take the bias. The question here is essentially for what L does this attack work? For what L is it that you can expect more than L plus 1 columns of this form? So if you look at the calculation, you can sort of think for each column, what is the probability that all the non-zero fall into this set of rows? And you try to do that, and you want it to be larger than L.
Essentially, if that happens, then you just get to solve a much lower dimensional problem.
Yeah, you get a much easier problem. And you get some parameter, which actually turns out asymptotically at least to be exactly the same regime as I mentioned earlier.
Sparse dense LPN during the sample distribution, where you make this unlikely.
Essentially, or yeah,
Like
I make this attack unlikely.
Yeah, just the idea that you're like, rather than sampling at random, right, with the same sparse, you would be like, well, actually, it's important to me that like I exit this rectangle.
Not quite.
Okay.
Yeah.
I'm curious.
Yeah. So how do we avoid this attack?
Yeah.
So the attack requires on a very important thing, which is that you can see the sparsity of the matrix. You can see which entries are 0 and which are not. If we just take, say, a linear transformation of this matrix, then hopefully we can try to mask this out. That's the idea.
I see. And that makes sense, right? You just pick a different basis.
Yeah.
Pick a random basis.
Essentially. So this is the assumptions in a nutshell. We mask this by multiplying on the left with some random but compressing matrix. So it's not just n times n, because we also found an attack with that, but it's n times some constant less than 1. So like, let's say n times 0.9, n times 2n or something.
Okay, now I'm a little confused. So does that have the effect that we talked about? Like that you're just transferring to a different basis, right? Because like what happens, right? Like, you know, any linear transformation is start with 2 bases. So like you can just like imagine that the first basis you start with like is just like the standard like E1 through En basis. And then you can describe like the same subspace. Is this like compressing linear transformation? So like is this like onto this linear transformation? Kind of like No, it's not. Yeah, it's a code. It has to update the rest, right? So.
Yeah, you can think of it like, so let's say you take each column. So you can reformulate this problem as, here you have a bunch of vectors. Let's say you have 2n vectors where each vector of length n. Then when you multiply with the sparse matrix, what you do is you essentially take random k-linear combinations of the vectors. And then you should show the result. You said, oh, sorry, k is still some constant.
Oh, okay.
Yeah.
Okay.
Yeah. So let's say you have these 2n vectors, and then for each for each result, you pick 3 random vectors among these, and you sum them up, and you give the result.
Yeah.
Yeah, and you do this many, many times. And the claim is that this resulting distributions will be pseudo-random, or at least it will satisfy the LPN assumption.
If it's pseudo-random, then the idea is that you can just appeal to like dense LPN.
Yeah.
Because you can't tell this from dense LPN.
Yeah, yeah. So that's essentially the appeal that's trying to make here. So yeah, also wanted to mention, if you know, there's this very old scheme called McEliece, and the idea is also similar. You start with some matrix for which, if you expose it, then the scheme is broken. But if you mask it somehow with some linear transformation, then the scheme is still secure for up until now. So it's been almost half a century, and then people haven't break it. Yeah. And so the point here is that now the construction still works for LTDF. Sort of the parameters still work out, because when you multiply things on the left, it doesn't change your image size. Because if m times x is already compressing, then when you multiply with anything, the image size is still compressing. Yeah. It's just that now we can plausibly say that this assumption is secure. So that's that. So that is our theorem. And we can also tune the parameters here a little bit.
So can you say what you have to like change the dimensions of the matrix? Because like to me it just seems like you can take the same matrix. Like, why did you have to change the dimensions of the matrix?
What do you mean?
Like you have this matrix M, and you want to mask it with a linear transformation. So I would imagine you can do this by just like changing the underlying basis of the code, right? Just like picking a different generator.
Yeah, so that would correspond to multiplying by a square t.
Yeah, but
right.
You did not do that.
I did not do that.
So why? Like,
why? Because if I do that, then you can actually try to find the inverse, and you will succeed.
Why would you succeed?
Yeah, I'll show you in a bit.
Okay.
Essentially, because when you try to find the inverse, you know that the target is some very sparse matrix. And so you have lots and lots of equations that are 0. And that means you can solve them easily.
Do like some like optimization?
Yeah, so we didn't quite analyze it rigorously.
But
we just, it's a vulnerability which is bypassed by choosing dimensions that are not equal.
Okay, so it essentially it makes the code like a worse rate code.
Yeah, it's worse rate, but it's
presumably
more secure.
Yeah, presumably, yeah.
Yes. Okay, awesome. So yeah, this is the theorem. We can also add in like any desired constant factor of lossiness. So let's say you want to lose by a factor of d. So let's say if d is 10, then you want to lose from say m bits to m over 10 bits, something like that, right? Then you can also get that construction from dense-sparse LPN with certain parameters. So here's sort of some concrete numbers for you to think about. It is quite bad, which is why this is not an efficient paper. But the point is that these are still inverse polynomial in the dimension.
And I think that regardless, like the motivation of like efficiency, I think maybe some people expect that like you make something efficient now, but I think the motivation of like making something efficient usually, I feel like that's pretty strong.
Yeah, I agree.
I used to use that in this grant. That's another thing.
Mm-hmm.
Yeah. So wait, I want to understand what we mean by lose, right? So I understand we go from like dimension like n to dimension, like
so
some inverse polynomials like n to the 1/2.
Mm-hmm.
But then like the question, but your map can still be injective because you're only mapping sparse. Is that true?
At some point when the range is less than the domain,
yeah, there's some balancing there, but like as long as your map can plausibly be injective,
then it should be injective.
Yeah, you need maybe some like constant gap.
Mm-hmm. Yeah, something like that. Okay, so let me try to go to this cryptanalysis section and just show you all the attacks that are present in the literature, and also one new attack that is particular to our setting. Okay, so the first is the generic attack in ISD, which I already told you the time complexity is exponential. And then there is a new attack here where you just try to find directly some sparse vector in the kernel. And such sparse vector actually exists because the M is a sparse matrix. So there should be some X that is sparser than it would have been if M were a totally random matrix. And you can try to brute force find this X, and that gives you some other attack, which is still subexponential attack. And then finally, you could try to just decompose this dense-sparse matrix. And if you succeed in that, then you have broken our LTDF constructions. But then we also show that with the setting of parameters that we currently choose, then we don't see any attack that is less than exponential.
So what's the thing? I'm kind of curious if you say a few words about like the sparse vector.
Oh yeah, that is next slide. So okay, next slide. So essentially right now the conjectured security is that it can go all the way to this log n over n, because essentially the dense-sparse matrix, we don't know how to distinguish it from random in any way. Okay, so this is the sparse vector thing, which is that if you just do the calculation, there should be a vector x such that when m is sparse, then n times x is 0, and x is relatively sparse. There's some dependency here between m and the sparsity, but yeah, you may take a while to parse this, but it essentially comes from this whole literature on constraint satisfaction problems and k-XOR and so on. But yeah, so this means that if m has this vector, then t times m would also have this vector, right? And essentially with random t, then the vectors can't be very sparse, which means that all the sparse vectors in the kernel of t times m are those that come from the sparse m. That's essentially it. And then we just try to find this x, but because there's seemingly no structure to this dense-sparse matrix, you can only hope to do that by exhaustive search for such x. Yeah, if you can find a better way to do this, then that would be amazing. Okay.
Wait, I didn't understand why it's important to find a sparse vector. Like, would you get find a sparse vector?
So
yeah, sparse vector in the product of t times m.
Then you can do the inner product with your LPN samples, and you can pick up any bias if the noise is too small. So yeah, it's just if it's LPN sample, then you have some error term E, right? And then it's essentially then you do like X inner product with E, and that would be biased if E has low enough noise compared to the sparsity of X. And yeah, that's essentially how you would detect it.
There's something. Okay.
Yeah. Okay. I guess this is the attack that I was mentioning. That, well, let's say we chose this to be just a random linear combination of a square matrix T, then you can actually try to find the inverse. Okay? You can try to find the inverse because if you look at individual columns equations, then you have A is known, and you try to find these Z vectors. But when you add them up, you get some very sparse vectors. So you can just get lots and lots of coordinates of this MJ, and you can assume them to be 0. And then that gives you lots of equations. Yep. It's not a rigorous proof, but it's sort of enough so that we had to come up with not square, but something sparse. So now if this is like rectangular, then there's some leftover parts that messes up the sparsity so that now when you try to solve for it, you no longer get something, the target is something sparse. You get something that is not. So yeah. Okay. Yeah, that's essentially that. There's also this technical thing about what if K is constant, then there's actually an inverse probability, inverse polynomial probability that the assumption is broken. And that just means the assumption is broken, right? Because the adversary can get lucky when you sample A in a bad way. Bad here meaning there is some very sparse X such that A times X is 0. And we need to avoid this a priori when sampling.
I see. Okay, yeah. Okay.
Yep. So this is actually
So, I mean, this is just
difficult problem.
This is saying that like a random sparse generator matrix is actually like not a good code.
It's not, yeah, it's not good enough for this purpose.
But I think that if maybe this doesn't help you, but like the parity check, like the matrix, the generator matrix with dual code, if like a sparse dual code matrix is still a good code with like inverse. Actually, maybe it's not inverse polynomial. Yeah, it's not inverse polynomial. Is K constant?
Yeah, K.
Yeah,
if K is constant.
Yeah, if K is constant, then it's not.
Yeah.
Yeah, but it's like essentially just one of those.
Yeah. Yeah. So you need some special distributions, and actually it's kind of a hard problem to find such distributions. We only know of one work so far that does this. It would be nice to have other constructions.
What do we want?
Yeah, you want this property that when you sample your k-sparse matrix M, then the probability that it admits some, say, constant sparse vector in the kernel is negligible instead of being inverse polynomial.
So, yeah, I mean, you can do that. I mean, you can do that. Essentially, you can like pick.
So you can try to rule out for a particular constant sparsity by just testing all the vectors up to that sparsity, but you can't do it in polynomial time if you want any constant sparsity, right? You need to do something.
Yeah, you need to pick
clever.
your matrix like to be kind of essentially. You would essentially be like picking a random Spielman. This is the way. I wonder what this paper did because that's what I imagine.
What about combiners? If you just maybe had 1 over poly, and then you did this many times, and one of them is probably good.
Yeah, yeah.
Yeah.
I think we didn't explore that too much.
The
One,
problem is, how would you combine it? Either you're
Yeah.
running
yeah,
with a lot-
combiners for
Yeah.
lossiness.
There's not many spots.
Yeah,
So-
combiners for lossiness is still kind of difficult.
Yeah, this is very related to the problem of building like linear time encodable codes. Like, that's one I like a lot.
Yeah. Cool. Yeah. Or
But
We
that's
can-
also just generally, if you happen to hit an M like this, then you get a lossy trapdoor function. So are there combiners specifically for lossy trapdoor functions, ignoring all of the details of
Mhm.
this?
I don't know. I think
Yeah. Interesting open question. So yeah, I guess this is a list of questions that I would love more progress on. First part would be this cryptanalysis. This is a new assumptions, and we really need to understand it better. Can we try to get any sort of reductions to other problems that we know about? Or can we try to get concrete parameters? This was from the top in crypto, but really when you try to do it, the concrete parameters are horrendous. So, yeah, you need like megabytes of megabytes to represent the matrix. Yeah.
Wait, did you actually try to implement this?
I try to compute the parameters, which is
Okay.
bad. Okay, so applications wise, there's a lot of primitives that we tried to get, but we couldn't quite get. And so it would be nice to do that. But one thing is that when you try to map the sparse M with the T, then you also lose some sort of functionality. So there are some tricks you can do with LPN that you can't quite do with dense-sparse LPN, and that's why we can't get these applications.
So we don't know some of these applications like Nithix from LPN anyway.
No, yeah, we don't. But something like Laconic OT or IDE is known from LPN with bad parameters, but we just can't do it with dense-sparse at the moment.
Do you think there are new tricks in dense-sparse LPN that will be useful, or is the
Yeah.
main advantage the different parameter regimes?
Yes, I think there are more things to be, to build upon, such as the nature of the trapdoor. Like this matrix has a trapdoor because it is
Right.
made of the product of two. Can we try to exploit that somehow? Yeah. And yeah, the coding theory question from the previous slides, I think it's also quite fascinating. And yeah, it would be nice to have progress on this. So
So what applications would you have if you have this solved?
what the application?
This coding theory.
Oh, the coding theory. So this is essentially you're trying to build polynomially unbalanced expanders with constant,
Polynomially unbalanced expanders.
with constant
Really?
degree on
you
one
think
side.
It has to be like,
Yeah,
just like it's you're trying to build a bipart that expands polynomially unbalanced.
yeah. So like n and then n squared. You can't have n and then some constant at n. So for that you can actually test and it's fine. But for our applications, we want polynomially unbalanced.
Yeah, it's interesting. I don't know. I guess I don't know enough about explicit construction.
Yeah, randomized constructions are good also.
Yeah.
Yeah.
But you want, well, I mean, what's the degree you're you have to degree.
What do you mean by degree?
Like what's the expander? What's the
Uh-huh.
degree?
Oh, I want it to be constant. So the
But how can you have a
K-
constant degree polynomial about what are your things when you like many of your vertices of the right be not they're not gonna be
yeah.
so you want
I'll
constant degree on the
yeah.
right, but like polynomial degree on the left.
Yeah, you want you have to have polynomial degree on the left. I would
Yeah,
say.
whatever the small.
Yeah, yeah. So, yep. So, yep, that is the whole talk, and thanks for listening.
Yeah, very interesting work.
Yeah, I agree. And I feel like this was like a really hard